round 4. Okay. So this morning we will have our jury starting from me and from 中原大学中原语 and then next is 中正大学谢立仪教授 and 嘉义大学苏忠教授台师大冯明光教授跟台师大韦世华教授。And I want each team introduce themselves. Okay, let me start from the reporter.
Hi, we're all neither from Typt American School. I'm Justin, this is Alex, this is Juni, this is Charlene, and this is Nico.
And the opponent.
Greetings, honorable judges and fellow opponents. We are Wei Ge from Taipei Legal Senior High School, and starting from the side we have Yangcheng Xian Shane Yang. We have Liao Zhenrui, Ray. We have Zheng Naiyang, Nathan, Zhang Naixing, Nancy, and finally me, Cai Yunxi, Catherine. Thank you.
And our reviewer.
We are family from Joshua Girls Senior High School, and my name is Yu, and this is Guo Shanyu, Guo Yunping, Zhang Yuci.
Okay, welcome. Okay, so we should begin our fight. The first the opponent will challenge the reporter for the problem. Number 1 minute.
The opponent would like to challenge question number 9, oscillating screw.
Okay. So the reporter, you can have 1 minute to consider. Yes.
We accept.
Okay, so reporter accept the challenge. So please write your representative name on the graph. Thank you. So reporter, you have 5 minutes to prepare, okay? But you can start anytime you are ready. How about the representative for the go right there? Okay, so reporter, you can have your speech. You have 12 minutes.
Hello, my name is Minok Chung from All-Nighter. Today I'm going to present on the oscillating screw. So the problem statement states that when placed on its side on the ramp and released, the screw may experience throwing oscillation as travels down the ramp. Investigate how the motion of the screw as well as the throwing of this oscillation depend on the relevant parameters. The main focus will be what affects oscillation or drag of oscillation. What parameter affects the motion of the screw? I'll go over the phenomenon investigation, theoretical model, experimentation, discussion, and conclusion. Phenomenon investigation. So as we roll down the screw from the top of the ramp, I'm going to use the camera stand to record the motion of the screw. So as screws slide down, there was oscillation, and then as the screw accelerates, there was a growing oscillation. Sometimes the screw stopped and it was damping harmonic motion, and sometimes the screw flipped, it was gap on its oscillation. So as you can see, the screw is in the damping harmonic motion when it stops. So the screw with the head and the tail is analogous to the cone, because when you rotate a cone is the bigger radius will rotate around the smaller radius. So here's some variables that I use for the theory. Let RT represent the radius of the tail. Let RH represent the radius of the head. Let L be the total length of the screw. Let R be the length from the pivot point to the head. And let RT represent the pivot point to the center of mass. Here are the variables that I use for angles. Let delta be the angle of the incline. Let the delta be the angle between the screw and the incline when you put the screw on the incline. Let phi be the rotational angle, and the theta be the angle for the pendulum motion. So here's the experimental setup. I use different type of ramp, which changes the coefficient of friction. I also use different type of screw, like different lengths and mass of the screw. So here's our data. So the cork board has lower coefficient of friction, and the wood has higher coefficient of friction. And as you can see, both cork and wood increase in the angle amplitude as time passes. And as you can see from the second graph, that wood, which has a higher coefficient of friction, went to a bigger angular velocity due to the existence of the torque. So here's the effect of the parameter of the motion. So we test 3 different lengths: 0.5 inch, 1 inch, 1.25 inch. So as we increase the length, there's an increase in the period. When the length increases, there's higher chance of stopping. When the length becomes smaller, there's higher chance of flipping. Theoretical model. So we make some assumption. The slip occurs at some constant beta for the equation, and only significant loss of energy is due to the friction. So so this is our main governing equation. E equals the potential energy plus translation kinetic energy plus rotation kinetic energy plus kinetic energy for the pendulum motion minus the work done by friction at given point. So this is calculation for the moment of inertia. So the moment of inertia for the pendulum is MRC cosine delta squared, because we want to find the horizontal component of the radius. And for the rotational motion, rotating itself, the formula is epsilon mr squared of the head. So this is our total energy equation. So as you can see, we account for the slip. So slip times r times omega phi equals to rc omega theta, because they're like the rotating motion and the pendulum motion have the same velocity. So epsilon, as I mentioned before, is a constant multiplied for I, and beta is the percent of slipping. So for the rotation kinetic energy, we replace omega phi using this relationship, and then the IR is the epsilon mr squared. For the pendulum kinetic energy, we just replaced IT with the moment of inertia that we derived in the previous slide. So this is the new version of the energy equation. Okay, so I moved the rotation kinetic energy and pendulum kinetic energy to the left side, and then I just solve for the omega theta squared. Okay, so let R1 represent the distance from the pivot to the tail of the screw. So R is equal to R1 plus L. And we know that the circumference ratio is equal to the radius ratio. So 2 pi r h, the circumference of the bigger head, times the number of rotation, to 2 pi r of the tail times the number of rotation should be proportional to r to r1. And rh to rt, r to r1, so you can find that relationship. Combining the first equation and then the fifth equation, you are able to get the r equals L over 1 minus RT over RH. Let T equals the proportion of R over L. So we can find the pivot point coordinate by doing 1 minus TXH plus TXT, 1 minus TYH plus TYT, because let's view this as a vector, so XH minus XP and YH minus YP is some magnitude multiplies the vector of XH minus XT and the YH minus YT. So the sum magnitude is R over L, and it will give you the length of the vector. So when you solve it, you will be able to get XT equals to XH 1 minus R over L plus R over L XT, and over L is the T proportion. So here's our experimentation and discussion. We found the center of mass by hanging the screw in the air and move the location of the string until it stops rotating. This is the data measurement for the table, for the experiment. So as you know that we use corkboard and woodboard, and then the coefficient of friction for kinetic and static are measured. And then we have a measurement for the length, width, and the mass of the screw, diameter of the screw, of the head and tail, and the duration. So here's analysis for the angular velocity. So we basically track the motion of the screw and see the data dot. So as you can see, as time increases, the data dot also increases. This is our calculation for the period of oscillation. So period of oscillation is for the physical pendulum, since it's not like simple pendulum because we have a mass for the tail curve, the length. So the formula for the period formula for the physical pendulum is 2 pi square root I over RC mg sine gamma, which is calculated to be 0.61 second. And then since the physical pendulum is assuming that there's no effect of friction, we just take the first beginning part because the effect of friction increases as the time passes. So the T expected from the graph is calculated to be 1 minus 0.17, which is around 0.83 seconds. As I mentioned before, the physical pendulum didn't account for the friction, and the definition of simple pendulum is a physical pendulum is free to vibrate without any friction. Now we use a constant solver to find the constant for h d dt squared plus f to match it with the theory. And then the a is equal to 5.01, b equals 0.974, c equals to 0, and f equals 2.4. So for the error analysis, we have a linear trend which shows the linear correlation in the values, and which reinforces the theoretical equation. However, the slope was different. If you go to the previous slide, the slope is calculated to become 0.42, but theoretically, the slope should be 1. So this is accounted because of the constant for the slip. And since we assume in the ideal model that there's no slip in the motion. Also, the y-intercept is not at 0. As you can see, the y-intercept is in around 2. So the initial angular velocity was not accounted for the theoretical model. Also, the coefficient of the velocity was 0, which means that the translational velocity is the one that moves the screw forward, and for the oscillation, it is due to the rotation kinetic energy and pendulum kinetic energy. It does not have anything to do with the translation velocity part. So there are two different components. So it shows that there's no effect of velocity on the oscillation. So this is our conclusion. In summary, the oscillation grows due to conversion of potential energy into rotational kinetic energy and pendulum kinetic energy. Despite the growing oscillations, the motion can stop due to the work done by friction. We performed analysis of how length of the screw and the friction coefficients between screw and length affected the motion of the screw. We verify our energy equation through graphing the relationship between omega theta squared equals to -2 gh plus 1 half dt squared minus ug cosine gamma d minus e over m divided by beta prime plus cosine delta squared rc squared. The error between our ideal graph and the experimental data shows how much the slip occurs. Thank you.
Okay, thank you. Now the opponent have question to the reporter. 2 minutes.
Good morning. Good morning, judges. Can you go to page 5? Okay. Now, would you agree that there is bending on the ramp?
No.
There is no bending, so you're saying that is okay. Can you go to page 12? Thank you. So why is there only points and not a line?
Because we want to see the increase in amplitude, not like a general trend of the points.
But if you did a higher picture slow-mo video and you analyzed it, it could be done with lines, correct? And it could be more correct, because you can see here, these do not account for your theory, but these are not the trend line that you proposed in your report. Would you agree with me?
Yes.
Okay, thank you. Can you go to page 26? You say that there is no account for friction. However, in your introduction, you said the biggest damping factor is friction.
Yeah, and the friction is accounted for the energy equation and in our theory.
Okay, and you said that here you cannot use the normal pendulum function. And why is that? Because there's a mass.
If you use the normal period, we are assuming there's no mass in the line, and we're assuming that the mass is at the end, right?
But the string, but the screw itself, there is an exterior apex, correct? And from the apex to your point of the shaft, there is no mass.
So you could apex and shaft.
Okay, apex. Can you go back to your page where you calculate the curvature? The center of your no, can you go back? Sorry. Okay, it's okay. And also, yeah, this one. There is no mass here, so you could say
there's
that.
a mass here. So
Yeah, but that is a normal pendulum mass of m.
But you can view this as a part of the.
Thank you.
So time is up. Okay, now the opponent, you have 3 minutes to spare.
It looks like it's that's from the camera.
Okay, opponent.
Morning, opponents, reviewers, and honorable judges. I am the opponent from Waco Art Doing. My name is Nathan. Today we'll be talking about problem 9, oscillating screw. So the problem statement is when placed on the side of a ramp and released, the screw may experience growing oscillation as it travels down the ramp. Investigate how the motion of the screw as well as the growth of these oscillations depend on the relevant parameters. And our team will put its focus on investigate the parameters and explain the phenomenon. So our phenomenon is their experience first growing oscillations and then their stop. The theory is that energy, moment of inertia, and friction will be considered. The experiment's relative parameters are the length of the screw. However, the reporter has too few parameters. The pro of the reporter is they provided clear experimental setup, multiple sets of data were presented, and performed error analysis. However, there are a few contacts as well. The screw analogy was too ideal, does not fit into reality. There are too few parameters were discussed, such as the size of the hat. They failed to incorporate damping factors into the theoretical model. Model exists errors, they're too idealized. The equations were not labeled, did not include units, they're too ambiguous. And the graphs presented were not well defined. So there are a few discussions that I would like to talk about. First, regarding the phenomenon, the bending of the ramp and the idealization of the screw as a cone. In our theory, the damping factor, there are more than one friction damping factor. The friction is the only significant one. The force of the energy loss, the moment of inertia, idealization of that. And on page 26, there are 36% error. However, you fit that into your theory. And other discussion points will be the normal pendulum calculations without a mass, the definition of apex in the experiment, the boundary conditions of this experiment, and your first graph analysis when you discuss the friction as your energy. And also, experiments, there are other relevant parameters such as initial angles, the ramp inclination angle, and also the size of the hat. Now I'd like to invite the reporter for discussion. Okay. So you can go back to page 26, continue where we left off.
Just for the clarification of the point and the line.
Yeah.
So since we're only done with the experiment, we just put the data points, and we didn't put the trend line because you can see the trend. You can see the trend from the points.
Okay, but there is, I'd say, if you took the video in a higher picture frame rate, you could create a frame line
I think
using points.
that's the point for like aesthetic. I think you can clearly.
It's not aesthetics because your trend line, not trend line, your points, they do not comply to your theory. So that's one thing I want to know. Because on page 26, at the latter part of your graph, there is a motion of the word M without touching the x-axis, and that's one point I want to discuss. Or if you could speed up the process, that would improve our discussion experience. No, neither. No. It's a nice one.
That's different.
With Ethan as a reporter. 26. That is a different part.
Sorry for the.
can you use the same PowerPoint and go to page 26? The same PowerPoint, not the one from all the no-nighters.
It's not it's okay if you like describe what's.
Okay, so your theoretical value was 0.61 seconds, correct? And then your experiment value was 0.83 seconds.
Yes.
There is, because it's a 36% error.
Yes.
How would you explain that? And how would you say that the theory fits if there is more than 1/3 of your data wrong or incorrect?
Can I use the whiteboard?
Oh, yes.
So for the simple pendulum, I alpha is equal to.
Yeah.
So I.
No, can you just explain why is there a 36% error and you still consider that as correct?
Because we didn't account for the friction.
The friction. Okay,
So the torque
yeah.
is only for the torque caused by gravity. We didn't include the friction
But that is a damping factor, and why would you not include that?
because we want to show if you include the torque in the inside the formula,
Yeah.
then it's not a physical pendulum anymore. Right? Because the definition.
Yeah, but you're too idealizing the reality.
Yeah,
to not fit. To not fit.
But the formula doesn't make sense if you include the friction.
Well, in
So
my opinion.
why do you even add that?
Because in my opinion, you can do something other than torque to idealize, not to idealize, but to fit the phenomenon. Because using torque and ignoring a big factor of friction,
Just to clarify, we didn't like ignore the effect of friction.
but you did not put it in your theory.
It is in the theory.
Okay, let's jump past that part first. No, I mean the torque theory. Because this part is where you have that 36% error. How would you explain that 36% error? You ignored the friction, right? That's what you said. And why would you ignore friction in this part?
So to clarify, is the I alpha. I mean,
You're saying the same thing, but why would you ignore that in your torque?
in the torque.
Yeah, here. That's where your 36% error
Because
comes
the
from.
definition of the simple pendulum is without any torque.
Yeah, but why would you,
If you
okay.
add it, then you cannot use the formula anymore, right?
Okay, then, can you draw a force graph of the hat and the shaft of screw?
It's in the it's
The direction of the friction, in specific. Can you draw that?
It depends on where you look. Which direction is it going? Is it like going for the pendulum motion? Is it going left side or the right side? It
No,
depends.
just choose one, it's okay, choose
Oh,
one.
let's say you go this side.
Okay. So that is your friction. That's the only
It's
friction.
a motion.
Okay, I want you to draw the friction.
Yeah. And then the screw is translating this way. Right? So
Yes.
there's a friction this way and to the right.
Can you clarify your 3D error graph?
Oh. This is the motion of the screw.
Yeah.
This is where it's like rotating.
Yeah.
So there's a friction this way to
It's friction, that, okay.
to slow down the pendulum motion.
Okay.
And there's a friction this way to counter the motion of the screw.
Okay, how about the two contact points? Because you idealize the screw as a cone. And on a cone, there is one side that is always,
To clarify, the analogy is for like easier to understand, not like exact same model. So there are like two different things. I just
yeah, but in
want
your
to
model,
say
you
that.
yeah, okay, to make it more easy, okay.
That's that.
So to idealize the screw, you use the cone, and you ignore friction, and you say that your theory is correct. Agree with me?
Only for this calculation because it's not part of the definition. I include in the governing energy equation.
Can you explain what this is? Why is there a transformation here without going back to the angle?
Oh, yeah.
No, just if you can explain.
Yeah, that is part of the slipping.
Yeah,
You know what the slip?
Yes, I think it's slipping.
Yeah.
But you did not account slipping here.
Because
So why would you put that graph?
Because as I said, the definition doesn't include friction, and then only the initial part kind of makes sense because there's
So you
a small
kind of
effect.
makes sense in this topic.
No, because the definition doesn't include the friction, as I mentioned like 3 times already.
Yeah.
So you cannot put the friction here to calculate the period.
Then why would you use this if it does not fit your energy theory?
That's why this shows there's a difference this shows there's existence of friction because there's difference in the value, right?
Okay.
So there's a discrepancy of 0.2.
Then what is
to
the
2.
value here of friction? Are you just gonna minus this and come up with 0.22?
Yeah.
Oh, so that's how you calculate. Okay. And also,
I'm just saying this shows there's existence of the friction.
okay, can you go to your moment of inertia slide? Because in my opinion, you say that you should use Sylvester's law of inertia to calculate your inertia. Do you know Sylvester's law of inertia?
Oh, no.
No, okay. So in my opinion, you could use this to really make your theory more fitter to the reality. So you would have Q as the rotation matrix, the initial moment tensor, initial inertia tensor, and then the transformation of the rotation matrix, which will make it fit reality more because there is 3 axis and there is rotation distance. And also, do you have any
Can
boundary?
you clarify like what the each matrix like
Okay,
represent in the? Is it like n by n, right? So what's the value? So you're bringing the matrix that you really didn't memorize. You understand. So that's the rotating, right? It's a matrix for the rotating. And YZ direction.
Yeah, that's it.
Reflection over X.
And is there any boundary conditions in your experiment?
What do you mean boundary condition?
Like at what angle does the phenomenon occur? At what coefficient of friction does the phenomenon not occur?
Oh no.
No, okay, you do not do that. Because in my opinion, if the friction is large enough, the friction should stop the screw from sliding down, and there only should be a pendulum motion at the top of your bending ground, or at your
You're
ground.
saying the translation energy is all lost by the friction.
If the friction is
There's
large
no
enough.
translation motion.
No, there is, if the friction is large enough, let's say this is the board, right? Your screw should only, your screw should only move like this without any downward sliding. Would you agree with me? No, would you agree with me?
Oh yes.
Okay, but you agree with me, but you did not do the boundary condition, correct?
Oh yes, because I didn't see that in the the experiment when I did it.
Okay. How about the
So for the high coefficient of friction, like what is the coefficient of static value? Because I just coefficient of friction 1.1, that's pretty big, but it didn't occur, right? So
Yeah.
what is your like ideal value for the coefficient of friction?
first of all, it's not ideal.
Like what's the boundary condition?
In my opinion, it really differs on your parameters, your few parameters that you presented.
For example?
For example, like the length, the angle, the moment of inertia, the correct moment of inertia, and then correct idealization of the shape. Okay, now I have another discussion I want to talk about is, why is there so few parameters in your experiment? Why didn't you include the hat size? Since in your graph, you present that there is this angle here, you had 3 angles, let's say phi, rotation, theta, and in the screw here you had gamma, if I'm correct. Or, no, you go back to the graph. You can go to the graph of your setup. Excuse me, you go into the graph of your setup. Slide, we had this triangle.
It's before the experiment at the beginning. Wait, so you mentioned we didn't consider parameter like size of hat, right?
Yeah,
But we considered the proportion instead.
proportion set.
The
How about the
key
length?
value. Sorry.
How about the length of this?
The length? The length is used in the proportion.
Oh, the proportion, because you idealize that as a color.
No.
Then how did, okay, then can you go to your...
So the cone part, let me clarify.
Okay.
So the cone part is just okay. So there's pivot points and there's screw rate. The cone is just to show that what's going to happen if there are 2 different radius. That's it. It doesn't it doesn't model like there's no like
in the slide, the other side, that you noted the angle between the hat and the ground. That one. No, not, oh my god, sorry. That angle. You should put that into your relevant parameter.
Which one?
This one.
Yeah, it's part of the moment of inertia calculation.
Like a good moment under calculation. Okay. How about the size? I mean, not the angle, but the size.
I'm sorry,
Okay.
time is up.
Thank you.
So opponent, you have 1 minute to summarize.
Okay, so I am the opponent of the Wicard, and now I will give my summary of our discussion. So first, the data does not comply to a theoretical model, and hence proving the model to be erroneous. And also, friction and damping factors were not considered in the model, causing significant error when the reporter failed to explain and kept on saying that they ignored the damping factor without saying why. And the slipping was used to explain the experimental results, yet as well it was not considered in the theoretical model, failed to mention any boundary conditions. Moment of inertia in the model was presented with too few considerations and too much idealization. It failed to explain why the idealization of the screw analogy was adequate, and the angle of incidence, angle of ramp should be considered as well. That would be the end of my discussion. Thank you, judges.
Okay, now the reviewer. You can have a question for reporter and opponent for 3 minutes.
First, I want to ask the reporter, can you explain why the period changes over friction?
Why period changes?
Yes.
It's the deep-plate system of friction.
So it's friction. And since your experiment included fact of friction, why didn't you adopt the formula in the theory? Yes.
As I mentioned before, I accounted for friction in the governing energy equation. I didn't include for the period calculation because the definition says so.
No, I'm saying that the friction in your formula of the theory, because if you do the experiment, you can try adding the fact of friction into it, right?
Yeah, the coefficient of friction is part of theory. You can see the omega data for theory.
And for opponent, I want to ask this, that formula also considered friction?
Oh no, that is only the moment of inertia.
Okay, so what kind of parameters would you measure when you do the experiments?
We measured the angle of incidence, the angle of inclination, the hat size, the ratio from contact point A, which is the shaft, contact point B, the hat, and then the center of mass in that ratio as well, and also different friction coefficients.
So what do you think you can add in further experiments?
I can add the influence of like air resistance or some other the force that takes over energy from the motion of the screw.
And so is the screw in your experiments, the hat is fixed or the size isn't the same?
What do you mean hat is fixed?
Like the hat and the screw? Because
Oh yeah, they're together, they're connected.
I mean, the size of the hat between the two screws, are they the same?
What do you mean, like radius or circumference, like
Radius,
radius?
right?
No, yes. Oh, sorry, it's like they're different. Sorry. So each screw has different dimension.
Each screw has different dimension, but you didn't talk about the effect of the dimension of screw, right?
I use the length of the screw in when I'm finding the pivot points, the calculation of the vectors. Yeah.
Okay, that's all.
Thank you.
Okay, so reviewer, you have 2 minutes to prepare your talk. Okay, reviewer, take it forward.
So high level reviewer, and then we're going to talk about oscillation screw. So first, the proper statement is when placed on the side of the rim and released, the screw may experience growing oscillations as it travels down the track. Investigate how the motion of the screw as well as the growth of these oscillations depend on relevant parameters. So the main focus is what affects oscillation and growth of oscillation, and what parameters affect the screw. This is the overview of the reporter. The pros are they explain the dimensions of the screw well, and they have clear theory and full formula, which I think is really good. But the con is they didn't consider the kinetic friction it may occur in the experiment, and they didn't show the trend of the oscillation, and they lack of experiments and worsening spending on the picture, and the theory cannot be concluded in experiments, and they didn't include bonding corrections. So the different parameters they considered is the material and the length, which means when the length is long, they have chance to stop, but when the length is short, the chance is to flip, but they didn't explain more about this. And for error analysis is the linear trend and the slope and the y-intercept. For summary, they talk about experiencing oscillation and stopping. And they explain the motion because of oscillations grows due to the conversion of potential energy into rotational kinetic energy and pendulum kinetic energy. And the theoretical period is 0.61 seconds, but this also doesn't include in his experiment. And for overview of the opponent, I think the process he considers different kinds of parameters, and he also considers the relation between theoretical model and experiment model. However, his formula, he also didn't say about the formula that considered the friction. So I think either reporter and opponent didn't consider about the friction, although the experiments, the friction affects very huge effect of the model. So the missing points are they lack of experiment process, and which means they didn't. This slide consider the friction. They also didn't consider some kind of important parameters since different sides of the hat may affect the friction. And they didn't talk about how to fix the friction either. And the model errors didn't fit the reality. So in my opinion, I think they could change their model by considering their own experience model and also minimize the friction. And they have two food parameters, but I think in further experiments they can try more on this. For discussion, they also talk about friction, but it seems like there's no conclusion about this. So in my opinion, I think they should try to use a smaller surface of the hat and smaller friction of the board. So to test the friction.
Time is up. All right, so reporter, your conclusion remarks.
Hello, I'm reporter from Oscillating Group. So in summary, the oscillation grows due to the conversion of potential kinetic energy potential energy into rotational kinetic energy and pendulum kinetic energy. And there's no effect. So despite the growing oscillation, the motion can stop due to the work done by friction. We also perform analysis of how length of the screw and the friction coefficient between screw and the ram affect the motion of the screw. So as you recall, there's an omega beta square formula, the formula that is derived from the energy equation, and then which includes the friction. So for the discussion, we talk about the motion of the screw, and then the opponents of the matrix calculation was too idealized and didn't consider that parameter into account. Also, for the coefficient of friction, they said at the high coefficient of friction, they will be only oscillating like at one location. However, even though I used coefficient of friction of 1.1 in my experiment, I didn't see any like observation of like during the experiment. There's no like the screw like going back and forth at one place. So the opponent said like we didn't include the dimension of the screw, but since we accounted for the ratio of t, and we find the pivot point using the t value, t proportion. So we do account for the dimension. Also for the definition of period, since it doesn't account for the friction, so the calculation of the period is still correct, but I do include the friction in the theory energy equation. Thank you.
Thank you. Another question from the jury.
Could you go back to the equation you used to show the energy of all the part of the problem? Because I need that.
Do you mind if I just write it over here?
Yeah, you can go ahead. Then I have to ask turn by turn which part is which part, because yes, okay, let's go ahead.
So the R represents for the rotation.
You don't have to go through the detail. Just first for the first equation, mgh is the potential energy.
Let me clarify. So this is the energy at one given point. So it is
True.
So mgh of that point plus 1/2 mbt.
What's BT?
BT is translational motion. That was
You mean go down?
yeah, only the screw going down.
Going down. Okay.
Not
The
rotating.
next one.
The R omega P is the rotation of itself. The axis screw and it rotates itself.
Okay.
The
What's the
pendulum-
last one?
The pendulum motion is there's a pivot and the screw rotates around the pivot bit.
It means it's rotating in this way.
Yeah, the
Okay.
period motion.
Okay. Why did you include the friction?
Because not only the friction is the most important part in the
Okay,
experiment.
let's do the one things. You have the one very big remark on your conclusion that the friction is included in the. Can we go to your final remark, conclusion remark?
Yeah, what I meant by that is there's a coefficient of friction over here, and I didn't account for the friction parts.
It means the friction is included for the energy. Okay, what's the role of the friction for both of you?
So friction would cause let's say, to go overboard on when the oscillation is happening and also stop. That's where the energy mainly goes away, dissipation.
That
So the friction will affect the motion, it goes down, and also the motion is oscillating.
okay. Would that be the kinetic friction or the static friction? Both of you.
Both.
And the last one.
It'll be both because there is rolling and sliding at the same time, so there would be static friction and kinetic friction.
You mean sliding down would be the.
Sliding down would be kinetic friction, and then rolling would be static friction.
Oh, me? Oh,
I think both is kinetic friction because
I think it's both because can't explain why.
It means both have you.
Both
Each
US
case will
and UK.
the static and the kinetic
Yeah.
will be both have the same.
Because if there's no
That's
such thing
good.
as static.
Just for the important, what's the motion of the center of gravity of the screw on the plate?
The center
What's
of
the
mass.
motion? What's the motion of the center of gravity of the screw
You mean the
on the
center of
plate?
mass?
How it travels? The center of gravity.
So the
You just mentioned the oscillation. How does the center of gravity moves?
So as it oscillates, the center of mass is between the head and the tail, right? Kind of
No,
towards
just
the,
you locate the center of gravity. How does the point center of gravity moves on the plane?
He's asking the question, the school, do you have the center of mass, how it move?
like it's like diagonal. So the screw rotates like this, right? And center of mass is
No,
here. So
the center of mass would, he's asking, the center of mass will be moved in what way?
So it will be in like a linear graph, like for the going downwards, yeah.
Just downwards or
Like
side?
in angle, yeah, in angle.
Jerry, may I use the board
Oh,
for
I
this?
just asked because he has experience doing the experiment. Okay.
Can I clarify?
Okay.
So it will go downward because the oscillation is going downward. Like the oscillation is going down, right? It's a pendulum motion is going down, right? So the center of mass will go down, but it will like rotate about the pendulum.
I just asked the center of gravity.
Yeah, so it will rotate about the helix.
Does it move sideways? Center of gravity. Does it move sideways?
Oh yes.
Why?
Like you mean like horizontally?
Just the center of gravity. You ignore the entire nail. You just concentrate on the center of gravity. How does it move? Does it move straight downwards or does it move also sideways?
Okay, so here's the incline. So the screw is going down. So the center of mass would go down because there's a translation reports, right? And then
I think he's
since there's
indicating
oscillation
that
part, it also
there is a horizontal motion.
sorry.
There is a horizontal motion in the center of mass.
It's evidence. There's
Go
also
down, but
horizontal.
also there is the,
Oh yes.
All right.
Okay.
May I clarify your question? Any short question? Okay, then let's make our mark. Thank you. Thank you. Show the grade. Okay, let's first show the grade for the reporter. Start from here, 8, 8, 7, 6, 6. All right, then the marks for opponent. 9, 8, 8, 6, 6. Then the marks for reviewer. 7, 6, 6, 6, 7. Okay, thanks. And we have some break. 2. Okay, the opponent, please change the recorder for the problem. Challenge problem number 5.
The reporter would like to reject from the movie.
Okay, reject. Please challenge again.
challenge number 6.
The reporter would like to structure rooms.
So, reporter, you have 5 minutes. And then you can start anytime you like. Please write down your representative name on the blackboard.
Okay, reporter, you may start your talk.
Good morning, worthy opponents, reviewers, and honorable judges. I am the reporter from Waver Earthing. Today I will be reporting problem number 6, magnetic mechanical oscillator. So the introduction is that secure lower ends of two identical leaf springs to a non-magnetic base and attach magnets to the upper ends such that they repel and are free to move. Investigating how the movement of the string depends on relative parameters. Our focus will be explaining the phenomenon, modeling a theory, and investigate the relevant parametric relation. So first, our theory and model. So investigating the single leaf string oscillation without any magnetic influx, environmental influx, I calculated the torque and using sigma as the bending stress, which comes from Euler-Bernoulli's theorem, bending beam. Same theorem, calculate the bending stress of the spring because it cannot be idealized as a normal spring. And with that, I did a small angle oscillation just to prove that my omega and my period is correct. And here is my experiment. So there is two theory and experiment values. Here is the theory value of 9 centimeter leaf spring, 11 centimeter leaf spring, and these are the experiment values. And the initial condition was 20 degrees from the from the y-axis. The length of the I, which is the moment of inertia of the string, is 0.11917, and then the length of the string, one of them was 0.11. Now the second is the magnetic torque, because there is a environmental magnetic influx caused by another magnet. So I chose this model because first there are limited conditions in this magnetic model where because of the closeness of the magnets and the breadth of the magnets, this model fits. So first I calculated, we came up with this model, and then we timed its arm because it is a torque. K here will be an angular function because different strings have different K values. And after timing, after multiplying the arm and then applying it to reality, we come up with this torque function. So our theory composes of two major ones, which would be, this would be the torque, and then this would be the bending stress. And this whole thing would be the magnetic field. And also this omega and period comes from a fixed magnet on the right side, because, I'll explain later. So the experiment here is that we did here initial conditions the same, and our theory was 0.151 seconds, experiment is 0.164 seconds. And here the R in our experiment here will be the distance between the two magnets when they oscillate. So why did I do a static experiment in theory? Is because when you add another angular function inside the oscillation of the right spring, it does not have a symbolic solution. So therefore we use numerical method to find this would be a symbolic solution, and we had to make one. And so we idealized it, and we exchanged the symbols into A and B to fit the angular function. So without a symbolic solution, we came with a numerical method, and this would be the graph from MATLAB when we did run the theory, and then this would be our initial conditions, the same, 20 degrees. M1 and M2 would be the dipole moments of two respective magnets, and the time of 4, they have I, the moment inertia, the same length, 0.11, and the distance will be 10 centimeters here. And however, the difference between the dynamic theory and the static theory is that the distance between the two magnets would change according to the K constant as a angular function. So further discussions would be the energy dissipation from the eddy current damping. And according to Lorentz force and Ohm's law, that we could put this, this J would be the damping would be current index times the plus the velocity times the magnetic influx density. And then using force, this is what another magnetic force model would be the current density times its magnetic influx. And then here, this V here would be the volume of my magnet. However, the V here would be the velocity. And then adding the torque L would be the length of my arm, as I said, the bend string. and here would be the torque. So this would be another further discussion we will be making in our discussion eddy current damping. Another one is how we measure dipole moment. So we use this law, and then the most important thing here is we can see that the distance between the measurements is proportion to the power of the magnetic influx to the power of -1/3. So my setup would be leaf springs here, magnets, micrometer to stabilize it, and then high-speed camera, tripod, and then tracker, MATLAB, and Excel. For Excel, I use this to run the spring's K angular function. MATLAB to run the graph, tracker to track its motion. And in my experiments, the first important ones I did was symmetry and asymmetry, because I wanted to see the energy transformation between the two magnets. So as you can see the symmetry, this would be magnet oriented. The symmetry here was that the energy transfer was quite even. We can see the increase in amplitude and decrease in amplitude, the decrease in amplitude and increase in amplitude here. However, in an asymmetry, you can see the uneven energy transfer as this one with the initial displacement. This would be less spring as originally bent here. It decays due to its own damping. However, there is no pattern in energy transformation to the right spring. And another relevant parameter that we did was length. So we did length here, as I mentioned earlier, with the oscillation. Right. And as in this graph, you can see why this length is important here is because length affects the arm and then the distance of the magnets. So this is the bending stress here, and it has an arm of would be this triangle, and this triangle will be similar triangle to the one up here. So we use functions to come up with the geometrical functions to come up with the arm of the bending stress. And also another important thing is it affects the distance between two magnets and when it oscillates. So therefore, this is one relative parameter that we thought was important to do an experiment on. And the other one is angle, since my torque is an angular function. So we did two types of angles. One is pi/9 with pi/6, which is 20 degrees and 30 degrees respectively. And you can see it's difference in theory and difference in experiment periods. This same initial function. And this is the theory that I based it on, because without a symbolic solution from the dynamic model, the only thing we could do the closest was the static model. And as these two proved that my dynamic model would be correct in presenting the whole reality situation. And that would be the end of my presentation. Thank you.
All right, thank you. So now the opponent, you may have a question to the reporter. 2 minutes.
So I would like to, as your chart, I want to know why the amplitude will decrease and increase.
Oh, sorry. Oh, because there is relative damping here. As I said, there is damping, but also the oscillation from the other magnet will cause this also the oscillation of the phenomenon.
So it's because of the magnet?
Yeah, magnet, exactly.
Oh, okay. Are you sure?
Yes.
And then I want to see your formula, your theory.
Dynamic or static?
Okay, this yeah,
This one.
this one. So could you explain the this one, this page? Did you derive it or?
So we saw it on a Wikipedia model of a magnetic function. However, when we did derivations, we found out that there was errors in it. So we did our own model. We built it up. This is the model we built. There were differences in this. In the Wikipedia model, this was a plus sign. This is a negative sign. However, when we did our derivation, we built our model. We found out in our situation, this would fit better than the Wikipedia model. And as you can see, m1.r, this is our the vector that we created between the two magnets. So m1 would be the dipole moment, and .r, this would be the function, because this would be the angle, and the same angle here would be phi. So we dotted that, and then this was the whole function that we created.
Okay, then your chart,
This one, or this one?
the amplitude. So why it will stop in the end?
Oh no, this is just because my video had a time limit.
All right,
Thank you.
time's up. So the opponent, You have 3 minutes to prepare your report. The opponent, you may take the floor.
So, hello, I'm an opponent from Queer Family Municipal Girls Senior High School. So problem statement. Secure the lower ends of two identical wave springs to the non-magnetic base and attach magnets to the upper end, such that they repel and are free to move. Investigate how the movement of the springs depends on relevant parameters. Okay, and the reporters' main focus are first, they explain the phenomenon with many theory and formula, and a relevant parameter relation. So the experimental structure. The theory is oscillation of single wave spring and magnetic torque. And experimental setup consists of V-spring, tripod, high-speed camera and tracker, MATLAB, and more. And data the analysis. However, their data analysis wasn't fit in the theoretical model. That's conclusion. Their conclusions say that the amplitude decrease and increase that well. And there are pros and cons for the reporter. Pros, they have well theory, and when they report, they shows good confidence. And their prediction to the theory, according to page 10 of their PPT, and cons. First, the lack of experiment model, and it didn't show the slope of the coordination of the amplitude. So I would like to discuss the theoretical model amplitude kept decreasing until the end, and I would like to know why their experiment model increased over time. And why will the magnetic oscillator stop in the end? And I would like to know if there are any energy loss. And, okay.
Okay, you want to move on the discussion? Okay, reporter.
So, could you first tell me if there are any energy loss in your experiment?
Yeah, the damping and the bending stress creates heat, and then the damping of the eddy current creates heat as well.
So, the energy loss is okay. So, how can the experiments prove your theory since your data, some of data?
Because the theory is a theory, the experiment is an experiment. There's a few differences here. However, we did calculate this and see that it was less than 5% error.
Oh, so your error is less than 5%?
Yes, correct.
Okay. Then, so what kind of, hold on. I want to see your setup. Okay, so your setup consists of lead spring, magnets, and micrometer. Any of the parameters deal with them?
Oh, okay. So the link is leaf spring, and then for the magnets, I measured the dipole moments, so that was one of them. Micrometer is to measure the thickness of the leaf spring, and then also I use it as a stand because it is heavy and it has precise measurements on it. And high-speed camera is to use tracker, where the tripod is to stabilize the camera, and the MATLAB is to run the theory. Excel is to perform data adjustment.
So you use MATLAB to support your theory?
Yeah, to run the graphs that I presented.
Okay, so how can MATLAB support your theory?
MATLAB is an application where you can put differential equation systems in there, and then it will run the graph for it. And then the graph I put it side by side with the model, the graph I got from Tracker, which is the reality and this is the theory, and you can see that yes, it does coincide.
Okay, so you put your data into MATLAB and
To run this graph, yeah.
to run this graph. Okay, so can you explain these two charts since they seem a little different?
Okay, so this graph, the blue one, you can see they're all blue ones, right? I put the color here to make it more obvious. The blue one here is the experiment graph, and then the blue one here is the theoretical graph. And you can see that this is the displacement of the string here, and this x-axis is time. Same thing here, y-axis has displacement, x-axis is time.
Okay, so I would like to know if this experiment has anything to do with simple harmonic motion.
You mean this one? Oh, yes, it does, because this is where I base my theory off. Because not only is there magnet influx in this experiment, there's also its own oscillation as consideration. So that's what I put here.
Okay, so in your experiment, did you change the leaf spring or magnet as your parameters, like different materials of this spring or different lengths of this spring or different magnets?
I did do leaf spring, the length of leaf string, and for material, this K, as I said before, is an angular function because different leaf springs have, even if it's the same material, just a different length, it has a different bending stress. And with this bending stress, it comes with a different bending moment, and this bending moment is this K I created with a angular function. And because I did experiment. One of them was a linear line of 0.1 theta. The other one was a polynomial, so therefore you can't, it is a constant here that depends on the material used, but you can't put a number here.
Okay, so if I want to know if the two magnets have different magnetism field, what will happen if
So as I said here, this is the one I think you're mentioning. So I put these symmetry magnets with the same length and then same magnet here. And here is the magnet with two magnets and one magnet, right? And now, this is when the dipole moment of the whole setup is symmetry. So you can see the even energy transformation here. This one would be the one on the right because there is no initial displacement. This one would be the one on the left with the initial displacement. You can see the decay and then the increase in amplitude. Here, the increase in decay in amplitude. And then here you can see the asymmetry with the initial displacement on the left, no initial displacement on the right. And you can see that yes, there is decay in the energy here. However, you can see the one on the right does not get even energy transformation. Therefore, there is no pattern here.
okay, so hold on. Can you pardon with this four chart?
Okay, so this is the y-axis difference. However, I'm hoping that x-axis is different because they are the same thing. As I'm seeing the oscillating period, right? So we clarify. This one is the one on the left with an initial displacement. Okay, so you can see that there is a decrease in amplitude, decrease in energy, the decay, dissipation. However, on the right, without an initial displacement, you can see that there is no significant pattern in its period because there is uneven energy transformation.
Okay, so I would like to know why the amplitude is this chart. There is a but in this chart there go on and on.
This is my relative coordinate. So I said you can see there is a coordination axis here. So this will be the length, and this I set this point as my origin, x-axis, y-axis. So for this relative coordination, the y-axis, I track this point. It's always above 0. However, I set this as my another axis. So when it oscillates, it goes between negative and 0. So therefore, this negative and positive. So therefore, this is 0 and negative, positive, negative, positive.
Okay. So okay. In this experiment, are there anything to do with periodic motion?
Yes, there is a period. I just wanted to state that in asymmetry without the symmetry with even energy transfer, this may be a boundary limit for the experiment.
Explain more.
Okay, so because here in the statement here, they only state that there are two identical leaf strings, right? And they don't say identical magnets. And they wanted to create this phenomenon. So I said, okay, there might be another boundary limit here. So we did symmetry versus asymmetry with non-identical magnets owing to the difference in dipole moment. And then we found a limit to creating this experiment is that when it's asymmetry, you can't create a perfect phenomenon as stated in the topic. Therefore, this would be one of the boundary limitations.
Okay, then back to page 2.
Page 2. Here.
This video is your experimental setup, or you look for it on the.
This is one of my experimental setups.
This is your.
Yeah, and this video.com is when I made it into a GIF. But yeah.
Okay, then. So this is your base to fix the leaf spring, right?
No, this is one of them because I want to create a fast one. But in my reality, I used micrometers because if I use the same base, there will create resonance between the two identical leaf strings. However, if I use micrometers, which are two separate bases, we don't have to account resonance between the two leaf strings. So that's why I use micrometer with that instead of a wood block here. But that's just for the presentation of the leaf string.
Okay, so in your experiment, did you change the distance between two leaf springs as the parameter?
No, because that leaf string, the distance between leaf string, is also related to the length of the leaf string. The distance between the base of the leaf string is also related to the length of the leaf string. So therefore, that length of the leaf string experiment here would affect the distance. Since in my dynamic theory here.
Uh-huh.
Here, the distance between the two, R equals D, which is the fit distance divided, minus this would be the K constant angular function. However, the angular function is also related to the length.
Okay, so do you think if you change the distance between two big springs today, the experiment result will be different, and how it will be different?
So it will be the experiments will be different because the period will be smaller, because energy transformation would be faster, and it can be seen here because as my length increase, the period. What was that? Right. As the length increase, the period it changes, right? And it will be the same thing because this is just a one-dimensional vector that I need to consider. So either I change this or I change the length of each spring. It all affects the distance between the two magnets.
Okay, and today, if you have time to multiply your experiments better, what will you do?
I would add this eddy current damping in my model. However, eddy current damping cannot be easily quantified. So therefore, there are, as I said, errors in our experiment theory because I think the main reason is with eddy current damping. However, it can be quantified. So this is the best we could find with the relation of eddy current damping, magnetic influx, and my theory of torque.
Oh, okay. You just said it can be easily to quantify.
Yeah.
Why?
Because eddy current, can I use the word?
Oh, okay.
Because the typical eddy current damping graph we see is that there is two magnets here, and then there is a string leaf, and it's a board. And now when it oscillates here, it creates a eddy current damping, which is it's a current here, right? And but in our experiment, it is the magnets that's oscillating between each other. And then with the oscillation, the torque affects the oscillation. However, I can't measure the damping, the eddy current
I'm
damping.
afraid the time is up.
Okay, thank you.
All right, opponent, please summarize the discussion. You have 1 minute.
I just asked some questions about their experimental setup and formula theory. Well, then asked if he can how can he modify his experiments better? And then I think their experiment really proves the theory that okay, that's good, and they didn't change the distance between two big springs, so I think maybe they can use it as a parameter next time.
All right, reviewer, please raise your question to the reporter and opponent.
Thank you for the discussion. So the first question would be, are the leaf springs connected by a single object for the majority of your setup?
What do you mean by single?
So for example, you mentioned how like you separated them into clamped to different.
Micrometers, yeah, correct.
Right. So was all of your experiments conducted using separate, like they were not connected together?
Yeah, they were.
Okay. So did you change the material of the leaf spring? And
We did. However, I did not put this as an experiment because it changes the, I said, the K function, the angular function, the angular function, and that is a constant that accords with the
okay,
angular
yeah,
material.
thank you. Are you aware that the Euler-Bernoulli only works for thetas less than 10 degrees?
Yeah, so that's why I added
Okay.
here.
As for the opponent, do you agree that when the magnetic field is directed to the other magnet, when there's a deflection, not all of the magnetic field is directed towards the other magnet?
Part of our less than. Part of our less than.
So for both of you, if when you deflect the strip, do you agree that not all of the magnetic field is directed towards the other magnet?
Yeah, so that's why in my model I created a new vector called R here, in which I dotted every dipole moment to the field. And
Okay, do you agree?
Yeah.
So do you think that investigating whether the movement is that of a typical coupled oscillator is important?
No, because in the topic statement it states that it should repel freely, so therefore you can't put in an external coupling.
Thank you. Do you agree with this? Or do you have your own?
Well, I prefer with the
Okay, so are you both aware that there is the movement first normal mode and versus second normal mode?
Yeah.
So do you calculate the damping constant?
No, as I said, we can't quantify eddy current damping,
Okay,
so that will be
thank
a further discussion.
So are you so you didn't find a way to calculate for the K constant, right?
I did find a way to calculate the K constant, however, it is a angular function, so it has to be calculated every single time with a different material.
So experimentally, how do you do it?
So I first, let's go back to the Bernoulli theorem. So do you know what bending moment of the supercapacitor point is?
My question is, like, did you
Okay,
find the
so I calculated bending moment of different leaf springs, and I used this function to find it. However, as my bending moment is a weight versus displacement, I used displacement. I measured the angle of the displacement, and I changed here the bending moment as a angular function. So these two are constant. The moment of inertia and the neutral axis is constant. However,
okay. So at theta equals 0, does the torque go into infinity? Is that true?
yeah, however, I'm using numerical methods, so therefore it can't be calculated.
But shouldn't you be using experimental methods?
No, I'm using experimental methods.
All right, sorry, the time's up.
Okay, thank you.
So the reviewer, you have 2 minutes to prepare your report. All right, reviewer, you may take the floor.
So thank you for the discussion. And so today, I'm Charlene, and I'll be reviewing for the problem 76. So the problem states, secure the lower ends of 2 identical leaf springs to a non-magnetic base and attach magnets to the upper ends such that they repel northerly to move. Investigate how the movement of the springs depends on relevant parameters. So the focuses are on restoring a magnetic force, disappearing beats, and external coupling. And so review the report. For the pros, it includes the phenomenon demonstration. It includes quantitative formulas, numerical calculations for period, torque, static versus dynamic magnetic torque, and mentioned Euler-Bernoulli's, a few parameter tests, length and angle, and for improvements, there were a lot of the diagrams were hand-drawn, so there were unclear force angle diagrams. There's little explanation for theory variables when determining torque. There's no measurement of the magnetic field. There's no correlation curve between experimental results and the theoretical model, only numerical comparison of the theory. And there is only an experimental best fit, no logical explanation of theory from fundamental physics principles. There's also a lack of sufficient parameters about the least free material, magnet, size, and strength. And so opposition pros, they did good about asking good questions about amplitude change. They asked about relevant questions on relevant parameters and asymmetry. The opposition could improve in time management during questioning. They don't address major flaws in theory, for example, when they're not based on the fundamental physics concepts. So key discussion, energy loss. The opponent asks, is there any energy loss? The reporter says, yes, damping from heat loss. Reviewer disagrees with the reporter. Primarily, energy is lost due to rod vibration or friction between the rod and block holding the rod. And so opponent asks, will the material about the material of the leaf spring? The reporter says it does not change, but different lengths allow for different bending stress. And the reviewer says the material matters. So the opponent says, what future additions to the theory could be added? The reporter says, incorporate eddy current damping. The reviewer believes it's not important as damping caused more by other parameters such as friction and leaf spring vibration. And so the reviewer asks, are leaf springs connected by a single structure clamp? The reporter says it's not connected to the principal. And so did you change the material of the leaf spring? The reporter says no. And the reviewer says, are you aware that Euler Bernoulli only works for theta less than 10 degrees? The reporter says yes. So the reviewer also asks, is investigating the movement of typical coupling oscillator current? Both say no. And so I ask, are you aware of the movement of the first normal mode versus second normal mode? The reporter responds yes. And so I was asked, did you measure damping constant? And the reporter says no, they can't quantify that value. And so the reviewer says, we asked, theta, as theta nears zero, does torque go to infinity? And the reporter says yes. And so the points missed are, the reporter uses angles exceeding 10 degrees for Euler's Bernoulli, which would cause deviations. And they should also investigate whether the movement is that of a typical oscillator to fully go through the entirety of this problem statement. They should also use a connecting rod to connect both strips and investigate external coupling due to the rod, as that is what the problem statement is talking about. And they should also find a better way of calculating K experimentally, for example, by adding masses and using Higgs formula.
All right, thank you. Now come to the concluding report, the remark for the reporter.
Once again, I want to appreciate the efforts of both the reviewer and the opponent and the attention of the jury. And here begins my concluding remarks. Data presented from different sets of experiments analyzed clearly fits into the theoretical model, with error analysis presented within 5%. And the base was, again, not connected, since if connected, it will create resonance between the two springs. And the measured environmental magnetic influx density measurements were smaller than 25 microteslas, which can be neglected. And further improvements, our equations presented did not include units, and that would be improved. And the additional of the quantitation eddy current damping factor into a theoretical model. We did use Hemmel's coil to try to quantify the eddy current damping. However, since the change in influx is significant, we can't quantify the actual eddy current damping in the experiment topics. And that would be the end of my report. Thank you.
All right. Now the question from the jury.
You mentioned that couple oscillation and almost normal mode, couple oscillation and normal mode, etc. How can you explain to the others? Because the reporter doesn't say these things.
Okay, so
Just in a few words.
right. So visualize that. Commonly seen phenomenon is when you put two metronomes on a coupled surface, right? Two metronomes. So metronomes. And even when they're out of sync, eventually, when they're on a coupled surface, they will eventually go into sync. And so this is essentially what would happen in this phenomenon when we connect it to a rod, like connect both on the rod. So I think that you could do that as well.
Okay, thank you.
That's it.
Question?
Yes. Yeah, well, for the reviewer, you talk about the the friction between two, then you said the eddy current is not so important, but the string, the friction of a string, when the holding right, that will cause the friction force right. But what kind of propose you would present to identify the friction, because we don't know which friction is which one. How do you propose the plan that you can investigate, or from the experiment you can tell which one is which? You understand my question? Because once they have the damping constant, he said that's the caused by the eddy current. You can say that's the string. How can you propose another experiment to identify which one, which data shows the string, the friction caused by the friction you holding that, or the eddy current? Yes.
To like experiment to
Yes.
Find the eddy current
Yes.
value.
No, you can propose some experiment that the energy loss is due to your proposal, which is due to the friction, or due to the eddy current.
Yes.
How do you propose such an experiment?
Never mind, go to the reporter.
So because my model is based on torque, and I put the axis here, so the friction is negligible since the distance between the friction and arm is small. So therefore, the eddy current would be more significant.
How do you tell?
Yeah, it's asking.
How do you?
Yeah, you
Can
can
you tell?
make some experiment to
Yes.
justify. Yeah, where is the loss come
You
from?
want to answer again?
Yeah, would I? Okay. So I was saying that most of the energy loss is due to like the vibration of the rod and also the friction. And so I think that what could be done is that they connect both of these strings on the same rod versus when they don't have it on the same rod. So you put it on this side. For example, this is one rod here and another rod.
Professor, can I elaborate on my or no? Okay.
Okay, no question. I have a short question for reporter. You have some simulation which you show that they somehow agree with your experiment. I just wonder, this simulation, you have any fine-tuned parameter in order to match your experiment results? Do you need to tune some parameter which you cannot really measure?
So the only thing that I did not consider in my theory was the eddy current damping. Other things that I could put into the theory.
So when you do the simulation, did you?
Yeah, I answered for initial conditions would be the angle of the left spring, the angle of the right spring, the angular velocity of the left and the right.
Okay. And another question maybe for all three of you. Other than the eddy current or some friction with the holding base, you consider, for example, the gravitational effect or the air dragging? How do you think about those kind of effect in your motion? Maybe anyone want to? Yeah.
So I feel like the torque generated by the gravitational force should be relatively negligible. This is because as we're using Euler-Bernoulli to model, so when we deflect the strip by a tiny bit, we can sort of assume that the theta angle should be around 0 degrees. And so since torque equals R plus F, like this would generate a torque value of close to 0.
Okay. So I think it's ignored, can be ignored.
So I think it can be.
How about you?
Can be ignored. That's all right.
So you. All right, no further question, and maybe Jory make the marks.
Thank you.
so let's show the marks for reporter. All right, 99766. Okay, the marks for opponent. 58665. Then the marks for reviewer. 99767. All right, thanks. And then we'll take a break and have a round 3. The opponent, please challenge the reporter.
We would like to challenge number 2, oscillating sphere.
Who's rejected?
Rejected.
Who's rejected?
Re-challenge again.
We would like to challenge number 8, Euler's pendulum.
We accept it.
Okay. Barbara, accepted. Order, you have 5 minutes to prepare. Okay, reporter, you may take the floor.
Okay, hello everyone. I'm the reporter Fu Xunyun from Team Family. I'm from Kaohsiung Senior High School. Today my problem is number 8, always pendulum. Okay, let's look at the problem statement. Take a slick plate of non-magnetic material and fix one diamond magnet on top of it. Suspend the magnet rod, which can be assembled from cylindrical non-diamond magnets underneath it. Reflect the rod so that touches the plate only requires age and resistance. Study the motion of such a pendulum under various conditions. And this is our main point. The connection between the period and lacing time of the pendulum and magnetism force. That's our experiment video. And is our outline. We'll talk the observation. Before the experiment, we watch the experiment videos and a series of analysis. We will review the articles and talk about some theories. And that is our experiment and discussion, our experiment setup and data chart. And in the end is the conclusion. Okay, observation. After watching the experiment description, we guess the magnetism force and that of a pendulum may influence the experiment. And this is the formula of magnetism force between two magnets. And we can see if we want to control the magnetic force, we can add some arc force between the magnets of between the magnets. And the distance, we can add arc force to control magnetic force. And let's look at some difference between normal pendulum and always pendulum. Normal pendulum we use light string to hang a bow and we release it. So the center of the mass is on the bow, and because the string is light, we usually ignore it. And the always pendulum mass uniformly distributes on all of the magnet road. So we think the normal pendulum and always pendulum are different. And the centripetal force of normal pendulum is from horizontal component of the tension of the rope, and the always pendulum is from horizontal component of the magnetism force between two magnets. And this is the always stick. I think the always stick have some commons and difference between all the pendulum. The energy of all this is a physics toy. The metal, if we release the metal disc and spin it, it will turn it on it. Like a coin will spin into the floor and will turn it. It's like and it's a sunken mirror. The mirror is only sunken mirror is not important, but it will turn like this, and the energy of swirling is the gravitational potential energy changed into the kinetic energy. And if there is no energy consumption during the rolling, the metal disc will keep rolling at a certain angle forever and will never stop. But in fact, because of the friction and air system, the center of the mass must get lower and the angle theta will get smaller too. So in the end, the disc will stop in the end. So we think the pendulum, normal pendulum plus always plate will equal the always pendulum. But there are some commons. It's our experiment equipment. We use magnets. This is an upright board, and 3 centimeter long magnet 5 is on the upright board, and the rectangle magnet is on the upright board. And we use tape to fix the magnets on the upright board. And we use several upright boards to control the magnet force. And we use timer to measure the lacing time. And we want to know the track of the pendulum. So we stick a ball and color it to find the period and use tracker to track it. This ball is very light, and we think we can ignore the mass of it. And this we found the lacing time and the magnet account. This magnet is the magnet under the upper report, and independent variable is the magnet account under the upper report. Control variable is the upper report account and the magnet account on the upper report. And we can see the more magnets are, the long lacing time is. This is 3 magnets under the upper report, 4 magnets under the upper report, and this is the 5 magnets under the upper report. And we didn't do the 1 magnet and 2 magnet because there are 2 light and it will be stick on the upper report, and when we release it, it will not move. And it's the second experiment of the lacing time and magnetism force. It's the first experiment of lacing time and magnetic force. And independent variable is the magnet account on the upper report. But this experiment also not only change the magnetic force, also change the mass and the length. So we will do other experiment later. But when we change the magnetic account on the upper report, it's on the upper report and account of upper report. And we can see at the magnet and we can see when we add the magnets on the upper report, magnet force increase and the lacing time decrease. Yes. And it's a second experiment about the lacing time and the magnetic force, and the independent variable is the count of upper report. And when we, as we mentioned, when we add the upper report, the distance will be long, and the magnetic force will be lower. And control variable is the magnet on the upper report and the magnet account on the upper report. When we add, and we can see when we add the upper report, the magnetism force decrease and the lacing time increase. This is one. And the amplitude and time. We can see the amplitude decrease over time. I want to say more about it. When we only use 1 upper report and 2 upper report because when we add to the 3rd upper report, the magnet is too small to stick the magnet. And conclusion is the magnet force increase and the lacing time will decrease. And the more magnets on the upper report are, the longer lacing time is. Thank you for your attention.
All right. Now the question from the opponent to the reporter.
Okay, thank you for your report. I would like to ask, did you account for the damping of the pendulum?
Can you speak again?
Did you account for the damping of the pendulum?
I think we didn't think about it.
Okay. Did you make sure that V field was not affected by the surroundings when you did the setup?
You say surroundings.
Yeah.
What means the surrounding effect? Can you take an example?
Okay, I'll move on. Did you measure the magnetic field at all?
Huh?
Did you measure the magnetic field at all? Interacting between the 2 magnets?
If you say the magnetic force between 2 magnets.
The field. Okay. So did you also calculate the dipole moments of the moving magnet?
The life of movement.
Dipole moment.
Dipole moment.
Did you calculate? Wait, no. So did you consider sliding of the magnet, which led to the change of axis of rotation?
Sliding of the magnet.
Yes.
To see when it is motion and it will move each other.
How about the acrylic boards?
Acrylic boards.
Was there sliding?
It will not sliding. We fit it on the chair.
Did you fit the data to your theory?
Theory.
Yeah. Did you fit your data?
Fit
your
the data
tracker?
the theory.
Or did you have a theory curve at all?
Theory. I think it's fit on the theory.
Did you account for the loss of energy due to damping?
To say energy loss.
Yeah.
Energy loss. I think quite energy loss because
Okay, I think that should be a yes or no. So did you account for the moment of inertia of the magnet? To calculate the torque of the magnet.
oh yes, I think yes.
Okay, thank you.
Okay. Now, declaration for the opponent, 3 minutes. All right, opponent, please take your floor.
I'll be opposing number 8, Euler's pendulum today. My name is Jimmy and I'm from All Nighters. So the problem statement reads, take a thick plate of non-magnetic material and fix a neodymium magnet on top of it. Suspend the magnetic rod, which can be assembled from cylindrical neodymium magnets underneath it. Deflect the rod so that it touches the plate only with the highest edge and release it. Study the motion of such a pendulum under various conditions. In the presentation, I'll talk about external disturbances, oscillation, and damping. So the overview of reporter's presentation was it demonstrated video it seems to capture 3D motion, which didn't play, but there was also clear experimental setup. However, the unclear phenomenon demonstration was also there, so I couldn't observe the cylindrical magnet of motion. Also, the magnets are uniform. The theory, they provided a proposed equation for magnetic force. However, the magnetic force equation was wrong, and they had no qualitative theory, as well as not utilizing the magnetic dipole moments, and they didn't have the right connection between the Euler's disk analogy. And they also did not determine the magnetic field and position of angle. They also did not account for the body-centered frame, which means the rotation by its own axes. They also did not account for change in axes of rotation. The experiments, they had a good experimental methods. However, the units were very unclear. They tested a few parameters like cylinder magnet length and the number of acrylic boards. However, there were very few data points to compare the data, and they determined amplitude decay. However, they did not determine magnetic field. Also, they didn't have potential errors and did not account for the magnetic sliding, and they didn't have enough parameters tested, such as release angle, initial angular velocity, surface friction, and cylinder magnet size. They did not quantify the results using quantitative theory. Their data analysis, they had correlated theoretical curve with experimental data for some experiments. However, there were no error bars and no quantitative correlation between the theory, and they discussed proportional relationships based on plate thickness and the length of the magnet. However, they did not include correction for magnet slipping, and it did not obtain much data. So some of our discussion points are going to be the theory. We'll talk about 3D motion and Lagrangian coordinates, as well as motion of inertia, friction and damping motion, and some of the magnetic dipole moments. And the experiments will talk about causes of sliding and changing distance, length, and number of Hall magnets. And we'll also talk about the release of the magnets in terms of angular velocity. For data analysis, we need to talk about the fitting data to theory and relating this data to conclusion. So I would like to move on.
Okay, let's move on to discussion.
So could you please play the video if you didn't play the video? I would like to see the video.
Oh, can I throw it? Can I try to throw it?
Yeah, sure.
And this video is in the angle of this. This is an orb, and we fix the magnet on it. This is a tape, and here, and we also fix it. And this is we put camera here.
Could you focus on the motion a little more?
Yes, okay. And we put magnet on here. So it looks like this. And this it moves like this. See.
Okay, what I want to emphasize here is when you have the magnet, right? And then you release from the top like this. So assume this is the magnet. This is how you release it, right?
Yes.
In this case, the axis of rotation is going to be this part, because it starts from touching this side, and the magnet is going to come down with this axis of rotation, like this way. However, when it comes to a perpendicular position with the surface, it clearly switches the axis of rotation, and when it goes to the other side, because of angular momentum, you're going to have a magnet that faces like this, which axis of rotation is changed. So there's this distance. How did you account for this distance?
I think this kind of motion will let energy loose, but what do you mean?
So you can use the formulas or whatever you suggested if the axis of rotation is the same. However, there was a clear translation of axis of rotation, which means you cannot apply the circular motion to here, right?
You mean this distance will change?
Yes.
Okay.
Okay, so what I would also suggest is that if you also film from the bottom, as you said you have a camera here, right? You can see that the magnet is gonna, if the magnet is like this, you can also see that magnet has this motion as well as magnet going this way. So you're gonna have the 3D motion not only captured from this angle only shows the simple motion of magnet moving side to side. However, if you film from the bottom, you can also see how it rotates this way, and if you also combine it with this one, you can track the whole 3D motion. So what I would suggest in your theory is, if you draw the Lagrangian coordinates as you might know, and then assume that this is the surface, and when you have the magnet like this, right? So this is the surface, and that side is the ground, and then you're gonna have also the rotation of the magnet around its own axis, meaning that when the magnet is there, it's gonna rotate like this. We can explain it using psi. Psi is gonna show the rotation of a body-centered frame, and then you can also express this angle using phi, expressing the angle with respect to this axis, which is, you can say z, y, and x, and then you can say this is the beta angle. So if you use these coordinates, you can use 3 angles to better show the magnetic pendulum motion.
Okay, so then you think we can, I can use this to demonstrate the location of the magnet?
Yes, as well as the general motion. Could you go back to the slide where you had the formula for magnetic force? So, as I noticed, that's not the formula that you use for the force of magnetism, right? That's the gravitational attraction between the magnets. So, could you clarify what you were trying to explain there?
Oh, okay. I think, yes. I think, I don't know but I think they're similar.
Okay, so this includes the 2 of the masses, right? However, I would say under the region of top magnets, there exists a field, magnetic field generated by the top magnet. So there's going to be a field here, which is expressed as B. So your force has to do something with expression of B, right? So you cannot really use the mass of the 2 magnets, which are relevant because it's going to impact the motion. However, the B field or the magnetic field is not incorporated in that equation. So I think you should modify the equation so that you can solve for the B field.
So think I should use the B not the force.
B to find the force. So express force in terms of B. And then I can sort of show how to do that. I'll do it very promptly. So we can start from this formula, right? When we explain it in different terms, you can have and then expanding this, you can get I of dx dy as well as the partial of B field. So when you this way you can incorporate the B field into the equation, and this is going to give the area of the magnet. So when I and A is both incorporated, you can find the magnetic dipole moment, which I was talking about in the question, and then that dotted to the partial of B, which is going to be like that. And then partial has to do with the gradient. So I suggest using your force as this function, which incorporates both the magnetic dipole moment and the B field generated by the top magnet here. And the magnetic dipole moment is going to deal with the movement of the bottom magnet. So that's the mu value here. So I would suggest using this one. Okay, so let's talk about some parameter tests. You said you tested different number of acrylic boards and different number of magnets as well. How would you modify so that you can think of other variables that can change the experiment?
Variables?
Yeah.
What variables do we need?
What parameters would you add to investigate the motion? Because, could you go back to the slide where you had the conclusion or explaining the motion? Because I think what you said in the presentation was you used periods, right? You said different periods are going to come after.
Sorry, I didn't say periods.
Yeah.
I say less in time.
Less in time.
Less in time. Less time means different when I resist the stick and into the
Yeah, so the time is also related to the periods of the pendulum. And then if you only use the periods, you cannot explain the general motion, which is the problem statement is asking you to answer. It's asking you to answer what the general motion is, not investigate the motion, not the periods or the time it takes to come to stop.
But I think the time is also part of motion.
Time is part of the motion, but if you have the time, how would you express the location or angular velocity of the pendulum after that? So time is only one way to measure. However, that does not encounter for all the theoretical analysis that you could fit your data into the model.
A proper statement only, yes.
Could you go back to the problem statement?
It only tells me to find the.
Okay. Okay, so we can move on from that because it clearly says that investigate the motion. So, how did you control your angle to be constant when you released it? So, talking from this angle.
When you say angle,
Yeah.
you say this angle.
Yeah, that angle.
Okay, I already release it here, and I didn't release it here, but I only try to release here, but I want to try to move.
So, what do you think the impact when there's this initial condition of theta angle not being equal to 0 degrees initially?
Initially, you say how it works.
Yeah.
I think will be move in this, and the theta will be lower over time.
Yes. So that way it's going to change the frequency of the pendulum and it's going to change the period as well as your entire motion. So, however, in your presentation you didn't account for this initial theta angle that you couldn't take it into account. So I would also suggest that when you use the parameter, right, you can also apply an initial angular velocity, such like omega vector, so that you can investigate how the pendulum motion is going to change when there's initial angular velocity or initial angle as well. Okay, so can we talk about data analysis? So go to the end of the slide. Okay, so the graph, the simple graph. Okay, so it just compares the data, the two data of the experiments that you reported through tracker. However, does it show that it's how you match it with your theory or theory curve that you have? And also the linear line is not going to model the damping, which eventually makes the magnet to come to stop, right? So I don't see any theoretical graph in that you can compare with your two lines.
Compare two lines.
Yeah.
But compare two lines, as I said at the magnet, and the magnet for increase and less than decrease, because if the
okay, but that's only the qualitative explanation. How would you quantify or make a theory graph that you can fit the two other graphs into?
So you want me to compare with it?
Yes. So that graph is missing your comparison between the data and the theory. Also, that's only showing your data collection and not, like, you never show the theoretical graph that you included or you solved for the formulas.
This is my charge, right?
All right, I think the time is up. Opponent, please summarize.
So to summarize our discussion, we had motion of pendulum, which the axial rotation is going to change due to the experimental setup, but that was not accounted for. And I suggest that using Lagrangian to depict 3D motion like that is going to help it. And there's also magnetic force formula, which was clearly wrong in the presentation, and they should determine and incorporate the magnetic field, which dictates the motion of the Euler's pendulum, into the formula to get the force equals gradient of magnetic dipole moments dotted with the B field. And you can also add additional relevant parameters because they only investigate a period and lasting time and does not investigate the general motion such as angular velocity or the position of the end of the magnets. If initial angle is not equal to 0, you can clearly see that the whole motion is going to be different and the angular velocity as well. However, that was not incorporated into the presentation. The data analysis, they need to fit their theory into their data to compare and prove that their theory does make sense, but there was no correlation shown in reporter's presentation.
Okay, thanks. So reviewer, please raise question to reporter and opponent.
Good evening, honorable judges and the opponents. So my first question will be addressing both sides in regards to the axis of rotation you guys just mentioned. So in regards to that, you both the opponent mentioned that the axis of rotation would change by like this.
The angular.
The angular angle. And what else? Like what motion would axis of rotation include? Like except from changing end angles. or that's the only motion you think? The wrong.
The gravity is what causes the angular momentum, and then it's gonna shift the axis of rotation.
But I think gravity will also influence it, and also I think the air system and friction will influence it.
Okay. And in regards to that, which kind of friction do you think is included in this phenomenon?
Friction between the magnets and the surface.
Which type of friction?
I would say kinetic friction when the magnet's coming down.
And the reviewer, the reporter?
Yeah, I think it's connected friction too.
Okay.
Can I say that?
No, it's okay. And the opponent mentioned about the Lagrange. And you do know that Lagrange cannot calculate magnetic potential energy, right?
Yes.
And for both sides talked about damping, and which factors do you think should be considered when we were talking about damping factors of the
Yes, I think we should talk about damping.
which factor? Like what factors should we consider? Like should we consider when we're talking about them?
I think mass is too big.
Okay.
I would say the friction in this line.
Okay, thank you. And for the acrylic board that the reporter used, does both sides think there might exist bending? Yes. Okay. And do you think adding more mats as parameters would be adequate for an experiment? Because you do know that it is not there. Like the thickness of the acrylic board is not directly proportional to your theory.
Also, we use the same operating board, so we can control it.
Okay, thank you. And there is a centripetal force when the rod moves its motion, right? What do you think caused the centripetal force? The reporter. Different?
Initial angle.
Initial, okay.
Oh, I agree with you.
It was you. And no more further questions. Thank you.
All right. The reviewer, you can have 2 minutes to prepare your report. Okay. Reviewer, take the floor.
Honorable judges and worthy opponents, this is the reviewer from the Waker speaking, and today we will be concluding problem number 8, which is Peory's pendulum. And as for the pros and the cons of the reporter, so for the pros, they clearly demonstrated the graph. For the pros, they clearly presented some graph with supported theory, and the experiments setup was presented clearly and various parameters was considered. However, no actual model was presented, which adds on to the confusion and ambiguity. And they failed to present any quantitative data. Their theories are extremely flawed, and they failed to present any experimental phenomenon. So we cannot make sure whether the result is accurate or not, and they do not provide any explanation in regards to the theories presented. And as for the opponent, they questioned on-point questions directly, straightly at the flaws of the reporter's presentation. They provided a lot of personal insight and proposed alteration and suggestions that might be made to the experiment. However, we do believe that they sometimes focus on too much irrelevant details. And discussion one was about damping. The opponent questioned whether if damping was considered, and the reporter said no. But we believe, as the opponent, damping should be considered, and two factors, one including the friction, and the other is the magnetic field that would cause damping. And second, the measurement of the magnetic field of the environment was proposed by the opponent, and the reporter said that they did not measure any sort of environmental magnetic field. However, we believe that this should be highly considered, as if there is a high magnetic field influx in the environment, it would significantly impact your experiment results. And the discussion 3 was in regards to the axis of rotation, in which the opponent says that the angles would cause changes, thus their theory should not apply, and we do agree with the opponent. However, there is a factor in regards to the axis of rotation, in which that the axis of rotation will actually slide, so it includes a sliding motion instead of simply just dangling from a one fixed point. Thus, the theory presented from the reporter is definitely flawed. And lastly was about the magnetic forces equation was entirely wrong, and we do agree, owing to the fact that it is a gravitational, that the equation presented was a gravitational force between two masses, and it does not comply with the magnetic force between two magnets. And as well, I questioned about whether there is, I questioned about the Lagrange motion, as the opponent had mentioned. However, it is to be noted that the Lagrange equation could not calculate magnetic potential energy, meaning that even though the opponent provided several insights in regard to Lagrange equation, it does not fully comply with the actual phenomenon, hence more improvements should be made in regards to that. And as well, for the friction part, we should consider both kinetic and static friction instead of just static friction and unanswered by the reporter, owing to the fact that we should consider the sliding motion of the rotation axis. So the static energy should be considered. And lastly, I asked about the centripetal force, in which the opponent answered that it is caused by solely friction. However, we do believe that it is caused by both friction and gravitational pull and magnetic field force. And that should also be considered when the experiment and the theory is performed. And that would be the end of my concluding remarks.
Okay, thank you. Now is a conclusion remark from the reporter.
I think this is a concluding remark, and I think the motion of the pendulum, I think it will move in round, it will move in like a circle like this. And this is the right mechanism for formula, but it's still connected with the distance and additional relevant parameters. I think initial angle when we receive it have initial angle when we receive we have to collect it. And data analysis, I think we do each experiment 3 times, but it's the average of the experiment, so it looks maybe lack of data, but I think it's adequate. And 3D motion, we also put the camera next to the pendulum, but I think this video can see the pendulum clearly, so we pull this video. Thank you.
Okay. Question from the jury. Yes.
Okay, question for because you get the wrong formula. Because my reason, you made two mistakes. mistake. So I want to ask you how to define your lasting time.
Oh, listing time, yes. Listing time, it means when I release, start when we release the magnet, and stop when we stop it. Yes.
Okay, so can you go to the a picture saying about the one magnet and two magnets? So what it is? Because your x-axis, this means the magnetic count. I don't know, because the small letters.
Oh, this is one magnet on arcade, and this two magnet on arcade. And when we add the magnet on the arcade board, the listing time getting short.
Okay, so these two lines, what does that mean?
These two lines. This is the magnet account. Yes, this is a magnet account. This is 3 magnets, 4 magnets, 5 magnets.
So this is a simulation line or data. I don't know why.
We put it together because I want to say.
Is this the experiment data or just for
It's-
us?
Experiential data, yes. It's really look like this.
Yeah, you should put the data point.
Data
So this
point.
is 59, right?
Yes, we have 3 points, 3 points.
Yeah.
This time,
Here.
the point there. That would be much clearer.
Any more question? Yes? Maybe I have a question, maybe for the opponent first. You actually try to derive some formula for the force.
Yes.
So this is the force you think it's driven this motion.
Yes. Magnetic force.
How about the dissipation of this energy is also related to this force or the other factors?
Dissipation of energy is not. This is only the magnetic force. And the dissipation of energy can be explained by the friction force.
Okay. How about the reviewer?
So as we believe that the axis of rotation actually includes some like sliding, like the rod of the magnet, and experience some sort of sliding movements. So as well, both static and kinetic friction should be considered. And in regards to that, the heat dissipation will come from like, since the rod is in contact with, say, the acrylic board used by the reporter, the energy dissipation was hence coming from both the movement of the rod and the rod's contact with the surface.
The question for the opponent, because the reporter mentioned that for different number of these magnets, sometimes this motion doesn't, there's no motion or the motion just stops. They cannot spin or rotate. How about your observation?
I would say when the magnetic force or the attraction between them is too big, it's gonna, like, for example, if the top magnetic field dominates, the bottom does not have, then it's just gonna straightly come to stop because the top is so huge, the field is so huge that the bottom cannot swing sideways, and then there's gonna be huge attraction on the perpendicular to the surface.
So at that time, at that moment, can you still apply this formula?
Yes. However, the magnetic dipole moment of the bottom magnet is going to be small, which causes no motion to occur.
All right, I don't have further question. If you don't have any further question from the jury, let's make the marks.
Thank you.
let's show the mark for reporter. 3, 5, 4, 5, 5. Okay, let's show the mark for opponent. 9, 7, 8, 7, 7. Let's show the mark for reviewer. 8, 7, 7, 6, 7. All right, let's finish the morning fact. Thanks, everyone.